In the last few lectures, we saw a nice connection between improper integrals and series via the integral test, right? We saw that if a series converges, the integral converges, and vice versa. Now, thinking back to improper integrals, we also had a nice theorem known as the comparison test. Let's recall the comparison test for improper integrals. If you have functions that are related in this way, then their integrals are also related in the same way. The integral from a to infinity of f of x is going to be less than or equal to the integral from a to infinity of g. And consequently, if the integral of the large function converges, in other words, if this is less than infinity, the integral of the small function will be less than infinity. Conversely, if the integral of the small function is infinity, in other words, if the integral of the small function diverges, then the integral of the large function, which is bigger than or equal to infinity, must be infinity as well. So the large one must diverge. We have exactly the same thing in the context of series. Think about translating this into series. We have the following comparison test for series. Suppose that terms an and bn are related in this way. Then their sum will also be related in the same way. And consequently, if the large one converges, if this is less than infinity, then the small one will be less than infinity. If the large one converges, the small one converges. Similarly, if the small one diverges, then the large one, which is bigger than or equal to infinity, the large one must diverge as well. Let's write that down. If Bn converges, An converges. And 2, if An diverges, Bn diverges as well. An equivalent reformulation of the comparison test for integrals, if you will. Let's see a few examples. Consider this series. I mean, you're certainly welcome to do the integral test here. It's a little bit of work, but it's doable. Understand that this is not a p-series, right? Because it doesn't, I mean, if these two terms were there, it would be a nice p-series, but I mean, it's not, and we cannot make it into one. So what are we going to do? We're going to apply the comparison test to this. See what happens. But in order to apply the comparison test, we need to establish some inequality. So you need to have an idea of what's going to happen to this series. Right? If you think that this series converges, you need to find a bigger one which converges as well. If you think that this series diverges, then you need to find a smaller one which diverges as well. Well, let's have a look at this and ask ourselves, what can we think? What should we think? What are our thoughts on this function? Well, I mean, again, if the 3n plus 2 wasn't there, this would just be 1 over n squared. It would be a nice convergent p-series. So we're going to start with that idea, right? Because n squared is the dominant term in the denominator. So this is going to behave more or less like a 1 over n squared. So we expect it to converge. Let's prove it now by the comparison test. Well, what do we know? We know that 0 is less than 2. Less than or equal to, I mean, no harm done here. And we know that since we're restricting our attention to natural numbers, 3n is also bigger than or equal to 0. So if you add the two things together, 3n plus 2 is bigger than or equal to 0. Now add n squared to both sides. If we add n squared to both sides, we get the following. And finally, multiply this whole inequality by 1 over n squared times n squared plus 3n plus 2. Or, if you prefer, cross multiply to get 1 over n squared plus 3n plus 2 is less than or equal to 1 over n squared. And now you see what happens, right? What do we know about this series? The series 1 over n squared converges. It is a convergent p-series. Where p is equal to 2, which is bigger than 1. So the larger series converges, so the smaller series converges as well. In other words, this series converges by the comparison test. Let's consider another one. Consider 1 over n minus 1. Again, I mean, you have many options here, but let's do a comparison test. We have to start with an idea of whether this converges or diverges. If you remove the 1 here, right, I mean, your denominator, the dominant term is n, so this kind of behaves, the denominator kind of behaves like n, So the whole fraction behaves like 1 over n. And what do we know about 1 over n? It diverges. It's a divergent p-series. So we have to establish an inequality. We're going to make this bigger than a divergent series. Negative 1 is less than or equal to 0. If we add n to both sides, we get this. And if you multiply this by 1 over n times n minus 1, which is positive if n is bigger than or equal to 2, so the inequality is preserved, and we end up with 1 over n less than or equal to 1 over n minus 1. And what do we know about the series 1 over n? The series 1 over n is a divergent p-series, where p is equal to 1, which is less than or equal to 1. So the smaller series converges, so the bigger series the smaller series diverges, so the bigger series diverges by the comparison test. Diverges by the comparison test. Now here's the thing. These worked out very well, right? I mean, the example I'm erasing, it was easy to make this less than a convergent series. Here it was easy to make that bigger than a divergent series. But what if it's not working out so well? Consider this. Here, the dominant term in the denominator is n cubed. So this kind of behaves like a 1 over n cubed. So we expect convergence. But in very much the same way as here, right? I mean, negative 1 is less than or equal to 0. So n cubed minus 1 is less than or equal to n cubed. And if you cross multiply, you get this. And now this is what we're interested in. But compared to this, this series converges. So if the small one converges, you can't conclude anything about the bigger one. It could converge, it could diverge. We don't know. You see, the inequality is going the wrong way. We would like this to be on the left of a convergent series. So here, it's more difficult. And that illustrates the issue of the comparison test. In the comparison test, you have to establish an inequality. And it isn't always that easy. Let's see what can be done here. What can we say? We can say that, so I mean, let's take that again. N cubed minus 1. And let me say this. So this was from the 2 to infinity. Let's say that 1 is less than or equal to n cubed over 3, right? You know that x cubed over 3 is an increasing function. You can prove that by taking its derivative on the interval 1 to infinity. And as soon as n is bigger than or equal to 2, this is at least 4, and it just keeps increasing. So you can prove that the minimum occurs at 2. Right? I mean, maybe I should make that clear. If we look at f of x is x cubed over 2 on the interval 2 to infinity, the derivative, 3x squared over 2, this is easily seen to be positive on that interval. So the minimum occurs at x equals 2, and what is the minimum? The minimum is 4. So certainly bigger than or equal to 1. So we have n cubed over 2 is bigger than or equal to 1. So now, interchange, or multiply the whole thing by -1. And we get minus n cubed over 2, less than or equal to -1. And then add n cubed to both sides. And this thing is really n cubed over 2. So now if you cross multiply, you get 1 over n cubed minus 1 is less than 1 over n cubed over 2, which is really 2 over n cubed. So now, this series is a convergent p-series, where p is equal to 3, bigger than 1. So the larger series converges, so the smaller series converges by the comparison test. And that illustrates nicely the issue of the comparison test. You have to establish this good inequality. Surely, there must be an easier way. There is, and don't call me Shirley. In the next lecture, we'll look at the limit comparison test, which is very similar to this, but doesn't have this establishment of an inequality. We'll see that next time.